case. And then just turn it.
And we'll make sure that, yep.
Set this here if it's not working.
Yeah, I think the data stuff, but I'm going to take whatever interests me. Probably next to this one. Yeah, I think Spencer's in. Oh, yeah. I know Joe does 15 out of 80 something. He's like, yeah,
Okay, welcome back. Today we'll be talking about the visualization alphabet, the basic building blocks of visualizations, but first we'll finish up this data lecture. But before we do that, I also want to introduce Anshra, who's going to be like our fourth TA. Do you briefly want to introduce yourself?
Hi, I'm Anishwa and I am a master's student in computer science. Hi.
Okay, so Anishwa will be helping us with mostly with grading, but we might add additional office hours with her in the later half of the year. And so before I talk about my theory lecture content today, I would also be happy to answer questions you have about like homework related things or T3, or is there anything unclear that you would like to discuss? Yeah.
When you go ahead and you create your SVG, is it okay if you also create a group under that that will automatically transform everything so you have a margin?
Yes, that's actually the right way to do that.
Okay.
Yeah.
Rather than doing like a group with a circle and with a line kind of paired with it as you showed in the assignment, could we do layers of all of the circles and all of the lines so that it's easier to make sure there's no overlap?
Yes.
I think we changed the assignment so that the point is to have circles and lines can be separate, circles and text elements cannot.
Yes.
So your text elements and your circles should be in a single group, and the XY position of that group should be affecting how those move together.
Okay, as opposed to having three separate layers. I always do it.
You can have two separate layers,
Not
which is line, two not three.
And it's also not clear what you mean by layer. Do you mean like group elements or just render order?
I mean three groups so that I can just move the group around each other.
Yeah. So you're not actually gonna get much out of packing the lines in a group because each line has a unique position at both ends, right? So you can do a global transform to get margins and all working. In a group, that's useful, but other than that, you'll probably have to place every line by itself. And what is important to get the proper layers working is that you start, like, draw the lines first, and then you want to draw the other stuff on top of it, like in the order in which you execute it. Yeah.
Is there a simple way to be able to remove the line from the root node?
Could you guys please pay attention? Thanks. Sorry, say again.
So with the root node, is there a simple way that you all want us to be able to remove the line from it that would extend from its from the root node to its parent? Should we just should we just draw a line that is obscured by the circle?
Yes.
Could we, okay.
I would draw it to the center of the circle.
Okay.
Yeah.
I'm having trouble reading in the JavaScript portion. Is it acceptable just to manually put in HTML the names of stuff and
No.
layer on top? Okay.
So the point of the assignment is really that you do this with JavaScript. You can go to officers, and this afternoon there's one more. You can also come talk to me after lecture if you have a specific problem, I can help you with that. Other questions? Yeah?
So when you're supposed to put your name and like all the information and then you rewrite that directly
Yes.
in the HTML? Okay.
And you can use the address tag, which is kind of the right way to do that, to add that. Okay. Other questions? Did you find the lab helpful? I'll call you anonymously. Okay, so before I go into this, let's talk about where we kind of left off, and I kind of briefly want to recap what we did here. So we talked about data and data types, and so we distinguished between data set types and data types last time, and our major data set types were tables, networks, fields, geometry, multidimensional data, tables, networks, fields, and geometry, and the subclasses are again these multidimensional tables and trees for graphs. And then we talked about structured versus unstructured data. Structured data are these data types. Unstructured data are things like text and video. And I said that we essentially, to visualize unstructured data, we first have to infer structure, which is not the topic of this course. Then we talked about data semantics, so that it's important that we know for each, for elements or for items or for the attributes what they actually mean. And we had this example, the spatial 7S pair, which is ambiguous until we have our table headers, which give us the information about what the data actually means. In terms of data types, we had these different things like items, links, attributes, positions, and grids. And then we went through those. We talked about items and attributes and their relationships. So the items are the independent variables, usually the rows in the table, things that are like actually unique in the world, like a person or a purchase or a car or a product or anything like that. And the attributes are observation about those attributes, like the height of a person, the price of a product, the products bought in a purchase, and so on. Skip over this. We talked about these different dataset types. I'm going to skip over this. And then I think this is where we stopped. So we were talking about attribute types. And now, the question that we want to answer in the next couple of minutes is, what classes of values and measurements are there? And this is important for us to understand because these different classes, there's different visual encodings that we use for these different classes. So the basics are categorical, or also called nominal, and these are essentially things that you can only compare equality. You can't say this is bigger than that, or this is more than that, or anything like that. So this is like categories. Like, for example, we have things like fruit, gender, movie genres, file types, and so on. And so nobody would try to infer an order here. Ordered ones, in contrast, do have an order, but are still mostly categorical. So ordered categorical is kind of what you should think of as if we talk about ordinal data, where we have things where we have a greater or less than defined. Think of things like shirt sizes, rankings, car classes. You get like a compact, a medium, or a full-size car, for example. These kinds of things, where you don't want to make like a statement about like a small t-shirt is twice as small as a medium t-shirt, but you can say a small is smaller than a medium t-shirt. And then the class, the last class is quantitative attribute types. Here we can do arithmetic, so we can do addition, we can do subtraction, we can actually have ratios and so on. And the classical examples here are length, weight, count, and temperature. And we'll talk about subcategories, especially for quantitative in a moment. So for quantitative, there's two subcategories, and that's something that's maybe not completely, I think the previous slide was kind of intuitive, but this is something that if you don't think too much about it, it's maybe not quite as intuitive. So we distinguish between interval and ratio when we talk about quantitative data. And so quantitative, like interval data, in interval data there are equal differences between successive points on the scale, but the position of 0 is arbitrary. And so an example for that is temperature. You know that 0 degrees Celsius means something useful, right? 0 degrees Celsius is the point of the freezing point of water at sea level. What does 0 degree Fahrenheit mean? No, so as far as I understand it, Fahrenheit was an Englishman, and this was like the coldest day in England that he ever experienced. And so he said, like, it's not going to get colder than this, and that's 0. So, what's 100 degree Fahrenheit? What's the reference point there? Body temperature, yeah. Which is kind of like a little bit arbitrary, but okay. And for Celsius, it's of course the boiling point of water at sea level. I don't want to diss the imperial system, but yes. The point here is that even like though like in Celsius you have like a reason for why it is at 0, it's not that 10 degrees Celsius is half as cold as 20 degrees Celsius. Right? This is just not a correct statement. So the question that you have to ask yourself if you want to distinguish between a ratio and an interval scale is, does 0 mean nothing? So like 0 degrees Celsius is no temperature. But 0 apples in my basket is no apples, right? So this is countable. Well, that's not the point, but counts they usually have like a meaningful 0. And so you never should try to express ratios between interval data types. Quantitative ratio data types, here the relative magnitudes of scores and the differences between them matter, and the position of 0 is fixed. So there's 0, there's nothing of the measured entity observed. Things like length, mass, age, weight, speed. So the year 2018 is our year scale interval or ratio. Interval, yes, because our 0 point is largely arbitrary, right? Kind of like a recap of these things, these operations are defined on these different data types. On nominal data, where we have labels and categories, we only can test for equality. So these would be things like college majors, are you enrolled in math or are you enrolled in computer science? These are equality tests, you wouldn't want to rank those necessarily. Then we have ordinal data types where we have order operations, so we can make expressions about equality and also greater than or smaller than. Then we have interval data where we can have like 0, like a location of 0 is arbitrary. Here we can do equality, larger or smaller than, and we can express distance. So we can say that there is a difference between them. Yeah?
The distance between two interval points could become a ratio type, right?
Could become what?
Could become a ratio type, right?
Yes.
If you cannot add two interval points.
Yeah, so if you have like some important point in of inflection, you could make it a ratio type, yes. But you would have to have a good reason for that. And then ratio types, you can do all of the above, plus also measure proportions. Okay, so quiz. What types of variables are the following? 50-meter race times. So who thinks it's interval? Who thinks it's ratio? Who thinks it's nominal? Good. So 50-meter race times are ratio because we start the race for everybody at the same time. So there's a 0 point when the race is started. The college major. guess? The Amazon rating for a product. Yeah, it's either ordinal. You could make a case to do like 4.2 stars, right? You could make a case that it might also be interval ratio, but usually you should treat grades as like ordinal data and not necessarily do arithmetic on that. So like GPAs are actually like a bad idea. IQ score. IQ score is like clearly it's numerical, right? Is it ratio or interval? Who thinks it's ratio? Who thinks it's interval? So why is it interval? Zero IQ, like it's IQ scores are designed to measure on like humans with a certain ability, right? Zero IQ doesn't mean zero intelligence. Like my cat clearly doesn't have zero intelligence, but will fail an IQ test. Yeah. Okay. A product name? No. Exactly. So another interesting point is sequential and diverging data. Here we have homogeneous, like sequential data is homogeneous from the minimum to the maximum observed in a data set. And diverging, in contrast to that, where we have two or multiple sequences that meet at some point, where I have like a meaningful zero in between. What am I showing here in this image? Anybody want to guess? Elevation, yeah. So, and what region of the world am I showing? Yeah, so I can show you another picture where I picked a meaningful zero. And so here zero is sea level, and there is that here we have a diverging color scale where we have start with a different color at zero, above zero, and below zero. And suddenly, of course, like this is the yeah, of course I want to do that, but that's kind of like the idea behind that, and you might have other data sets that are like that. So here in this case, you see that in an elevation data set, clearly you want to have a diverging color scale for above sea level or below sea level. For example, for the state of water at sea level, you could have like a three-part color scale, right? Below freezing, essentially in solid form, in liquid form, in gas form. That would be a reasonable color scale for water. Other structures that we often observe in data sets are cyclic, especially when we talk about temporal data. Temporal data is quite cyclic. So here on the right, I'm showing a circular visualization of respiratory disease cases. People in Germany, I think it's that went to the doctor for respiratory diseases. And you see that the red here corresponds to a higher frequency of people visiting the doctor than the light yellow one. And so if I find the right pattern, you can actually see structure here. And what do you think the structure is? Seasons are here. It's actually weeks. And so people go to the doctor more frequently on Monday than on Sunday. That could be because they want to get out of work, or that could be because they couldn't go on Sunday and had to wait until Monday unless they want to go to the emergency room. And so therefore, Mondays are commonly busier for doctors. And then another important point to think about is that I have patterns at different levels. So here I'm showing you for two different types of aggregation. This was like a Google Analytics plot of the usage of our course website a couple of years ago in 2013. And so you can see essentially here is the beginning of the semester, we have a peak, and then here it trails off, and then the summer. Nobody was interested in that. And then what I can see though, if I zoom in, this is a yearly view, and if I zoom in, I can see more patterns where I see individual weeks and weekends. So these are just you can discover these patterns on multiple levels. You do have to aggregate usually to represent that. And so you really have to be careful about how you aggregate that. Okay, so now let's do this in review. Here we have a table with orders, an order date, order priority, product container, a base margin, and a ship date. We have the items are independent variables in the rows. Then we have the attributes, dimensions or dependent variables or features in the columns. Then we have the semantics in the header of the column. Here, like this is essentially what tells us what is shown in the data. Where are the keys here? What's the key of this table? So look at order ID closely. What's important about a key is that it's unique. Yeah, and so we actually have duplicates here. Like here in this order, like we have multiple products that are being ordered that can even be shipped in multiple separate boxes. So order ID is not the key. So the key here is implicit. The key is the row number. Okay, and now attribute types. Nominal, ordinal, ratio, or interval. What is order ID? Could be ordinal, could be nominal, but if you look at the order date, we see that actually order ID doesn't really correspond with the order date, so my guess here would be nominal. What's the order date? So order data here, different things. Who thinks it's ordinal? Who thinks it's interval? Who thinks it's ratio? Okay, I'll give the solution later. Here we have the here we have order priority. Ordinal, yes. Product container. Ordinal. Product base margin. Ratio, correct. And then ship date. And so here, like I'm actually not distinguishing between ordinal and interval. So it's quantitative. Like we had the order date, and we talked about time, especially date, being more interval. And then we had ordinal. We identified that correctly, categorical in the first one, and then numerical for ship date or ratio for ship date and product base margin. Okay. Then we also need to distinguish between our data model and our conceptual model about the world. Our data model are usually low-level description of the data, and where we have a set of operations that we can use. For example, we can say float, and we can use plus, minus, division, and multiplications. And our conceptual model is a mental construction of these data types. And that's really about supporting reasoning and about including semantics. So the data could be like 1D floats, the conceptual model could be temperature. The data could be 3D vectors of floats, the conceptual model could be space. And so what that also leads us to that we kind of have multiple levels of a conceptual model. So we could start out with a data model, a sequence of floats, then we apply a conceptual model to that, temperatures, in this case in Fahrenheit I would say, and then we can say to a data type, either like continuous to 4 significant digits would be quantitative, hot, warm, or cold would be ordinal, or burned versus not burned would be nominal. So we can do these transformations flexibly. And of course, in practice, like we've talked about all of these data types and data set types in isolation, but in practice, most of the interesting questions that we have to deal with are combinations thereof. For example, a network can have attributes about the nodes and the edges. Attributes can have hierarchies. Data types can be transformed, which is, we'll see, a very important property. Like very often we don't want to work with the raw data, but do some data transformation to actually be able to answer questions. And so, as always, we kind of conclude that real life is more complicated than just like our simple textbook classification. And in practice, it's often not as easy to spot those things, but still these things are quite useful. Okay, so now I want to move over to the visualization alphabet, marks and channels. Okay, so How can I visually represent two numbers? Let's say 4 and 8. Just give me some shout out some suggestions.
Line chart?
A line chart. So I could do something like this would be 4, this would be 8.
Roman numerals?
Sorry?
Roman numerals?
Roman numerals, yes.
Is it cheating to say Arabic numerals?
Like maybe raise your hands. Sorry.
Sorry. Is it cheating to say Arabic numerals?
No, it's not. You can definitely say 4 and 8. And I'm not going to draw like other bases. Yeah.
Apples.
Apples. So let me draw apples as dots. Yeah.
Be a bar graph.
Could be a bar graph.
Pie chart.
Sorry?
Pie chart.
Pie chart.
Tally marks.
Tally marks. I think that's very similar to that, but yeah. Binary. No other bases. We'll stay pay base 10 for now, okay? Yes, but dice faces. Okay. So that's kind of like an abstraction of these. Other ideas? Yeah.
Size,
Size. 4. What should I use for size?
anything, smaller object is 4, the double size is 8.
Okay, I'll make it a circle. Nobody has. We've only talked about shapes and multiple items so far.
Quadrilateral
Sorry?
using quadrilateral in octal.
Coordinates?
The quadrilateral, like for both sides of octal and polygon sides.
I don't
And octagon, like polygons, we use polygons for each other.
polygons.
Like a plan.
Yeah,
Like,
okay.
oh, yeah, okay.
4 sides, 8 sides.
Yeah, 4 sides, 8 sides.
Yeah, you can
Okay.
you can write a square for 4 and an octagon for 8.
Yes, okay. Oh, octagon. Probably not right.
You would probably need a legend, but you could use blue for 4 and then red for 8.
Can you?
If you have a legend.
With a legend, okay. Yeah.
How much is 4?
Like,
Yeah.
So sorry.
Saturation or brightness.
Yes, that's a good point. I'm gonna use texture to simulate that here. Okay, other ideas? So I guess even with a little bit of brainstorming, we came up with a fair number of different ways to represent them, and I would argue that not all of them are equally good. I think that's not hard to argue. So when we think about those basic visual variables, we call those marks and channels. And so marks represent an item. Remember, these are our rows or independent variables from the data types, or links, connections between two items. And channel change the appearance of a mark based on an attribute. Remember that the attributes here are the dependent variables. So if we have person A, that person would be a mark, and if the height of the person, that would be would encode that in the channel. Channel is also called, especially in a little bit older literature, it's also often called visual variable, and sometimes also aesthetic properties. I think in R, in ggplots, they call these aesthetic properties. So what are the marks for items? We have these basic geometric elements like points or lines or areas. You could also use volumes, but in practice that's not a good idea, and we'll be talking more about that. For links, we have these things that we talked about in the perception lecture, containment or connection. So these are our item type, our marks for the links. And then containment can also be nested. Here is like an Euler diagram where we have multiple relationships, who is friends with whom, or who is a clique, or who work in a team, or anything like that. And of course, it can be part of multiple of those. The channels, also called visual variables, they control the appearance proportional to an attribute. And so here we have, like these are of course not all of them, but these are the ones that we commonly use. We have position, color, shape, tilt, size in terms of length, area, or volume. And so these are kind of like our basic visual variables. This goes back to work by Jacques Bertin. So if you like study visualization as a field a little bit more, you will find a lot of work going back actually to his early writings, especially these like formal thoughts about what things mean. He was a French cartographer, and he wrote the book Semiology of Graphics, which is kind of like one of the foundational textbook of visualization. And he came up with these theoretical principles for visual encoding. This is kind of the table that he has in his book. It's in French. Here's the translation. It's position, size, gray value, texture, color, orientation, and shape. And so you'll see that our previous list texture isn't in there anymore for various reasons. I'll talk more about those later. So how can we use marks and channels? Of course, like it depends on the data set we have and what we want to say about it. So in this case here, our marks are lines. We have the channel here, so length of the line, and also the position of the line in X. And we map one quantitative attribute to the height and one categorical attribute to the position. You could like think of the categorical attribute in this case either being the items, but it could also be like the aggregate of something else. In this case here, the marks are the points, and we use only position in two different ways. We map two quantitative attributes, we use the X and the Y position, and then we get a scatter plot. If we add hue, we can use an addition, we can encode an additional categorical attribute. So here we will have like for two categories and two quantitative, or here we map like one categorical attribute and two quantitative attributes. And then we can add size, that adds one quantitative attribute. And this is like you will be implementing a scatter plot like this for your homework 4. So that will have all of these 4 different channels. You can also use redundant encoding, and sometimes that's quite efficient. Here I'm using length, position, and value. And so length is kind of obvious, the length of the bars. Position here is the top of the bars. Basically, we have created a baseline here, and then the position here, the positional encoding here is the top of the bars. And then value is like the darkness of these bars. The higher bars are darker. So here I use a threefold redundant visual encoding for this bar chart. Is this a good bar chart? I found this picture on Twitter on a day where there was like a ton of snowfall in Boston. The thing is that usually like television channels try to be like hyperbolic. But in that case, they were actually understating it quite a bit, right? Before January 23, there were 5 inches of snow, and after, there were 71 inches of snow. So it looks like 71 is about twice as much as 5. So the rule for channels is use them proportional to the data. We'll talk more about like what has gone wrong here, and when we talk about design and how we design visualizations to faithfully represent the data. So if we classify like these channels, we can actually classify them into magnitude channels and identity channels. And in magnitude channels, we map to ordinal and quantitative data. We can ask questions of how much or which rank. So for ordinal, how much, for ordinal, which rank, and for quantitative, how much. And these are position, length, saturation, and so on. And identity channel are what we use for categorical data, for categorical/nominal data. Here we can ask the question, what is it? And we can use things like shape, color, and spatial region. Notice that shape and color does not appear here, and vice versa. So you cannot. There are channels that are good for either one or the other. There are channels that are good for both, like position, for example. I can use position to encode categories, like all of the items of type A are in bin 1, all of the items in type B are in bin 2. I've separated them by position. But I can't use color to encode quantitative data. Yeah?
So when you say spatial region, is that similar to position?
Yes. And so this is the table from our textbook, and I think that is a very useful chart whenever you want to design a visualization, or I basically mentally look at this image, and then I ask myself the question, what is the data that I want to encode? Is it a quantitative attribute? And then I think about what is my most important thing that I want to show about this data set, and then I use the highest possible, this is a ranked list, so I use the highest possible channel. So the most important attribute in your data set, if it's quantitative, should usually be encoded by position. If it's qualitative or categorical, it should be in the spatial region, or color as a second choice. And of course, if you encode multiple things, you will not be able to use all of those channels anymore. And you can arbitrarily mix and match, right? There are restrictions and limitations in how you can combine them. So let's take a look at this chart here. So what are the visual variables that I'm using here? So the data is how, the size of the companies or the, let's say, value of the companies and how much tax they paid at their tax rate. And so we give those data types, and there's another data type which is industry. And so how are those different things encoded? Color encodes what? The tax rate, yes. Is this a unique encoding? There's this spacing or the positioning. So basically, color here gives us a binned idea of where a company roughly falls into, but their position along the x-axis gives us a pretty precise reading of how much tax, what's the tax rate for one of those companies. What is the meaning of position in Y?
Relative tax rates.
In Y?
How many
In the height?
How many there are at that rate?
Yeah, how many there are at that rate. But it's actually quite informal, right? It's not you can't, it depends, how many also depends on the size of the company. So I would actually say it's not a precise encoding in that case. What other channels are used in here?
So we're watching on the size of the pen.
Exactly, the size of our circles or bubbles is meaningful. And so we can actually separate this. What have I done now? What additional channel am I using now? I have a categorical data set now. I split it up by industry. And how do I show this? Spatial region, yeah. So I'm using spatial region here, or position, to also show these categorical attributes with industry. So this is quite a well-designed chart, I would say. And it's also quite interesting to see what kind of companies are actually paying a lot of taxes. So utilities don't pay a lot of taxes, which has maybe some public interest reason. But IT, for example, that's kind of odd, right? Apple paid 14% taxes, one of way below the average across companies. And if you look at who are the high payers, it's insurance companies and energy companies. They pay high tax rates. So we can also think a little bit more about the characteristics of each of these channels. And so we can come up with a couple of properties of these channels. And so the first one is selectiveness. Is a mark distinct from other marks? Can I clearly tell it apart? If I have two marks that represent a different value, can I clearly make the distinction? Can we make out the differences between two of the marks? Is a channel associative? Does it support grouping? Like obviously here, spatial region or like position does support grouping, but maybe some others don't. What is it quantitative? Basically the question, is it a magnitude versus an identity channel? Can we quantify the difference between two marks? Order, can we see a change in order easily? And length is how big is our vocabulary? How many different values can we encode with that visual variable? And we'll see that those actually vary quite a bit. So position, as I already said, is the strongest visual variable, and it's kind of the most important choice that you make as a visualization designer. What is your position in your data set? And it's suitable for all types of data. The problems that you have with position is that sometimes it's not available. So for example, if you want to plot data on a geographic map, your position is already used up for like the geographic locations. And so you cannot use position to encode an additional quantitative variable. And it can also lead to cluttering. For example, if I have, like in this previous chart, if I have a lot of companies that have exactly the same rate, then I have problems with like mapping that, especially if I wanted to plot a second attribute of that. So in a scatter plot, it's quite common that I have many dots that overlap over each other. So is it selective? Can I tell it clearly apart? Yes. Is it associative? Does it support grouping? Yes. Is it quantitative? Yes. Is it ordered? Yes. And we have a pretty big space. Like we can see like a lot of different positions on our screens. Here is like the classical example. It's a scatter plot. Here we have a couple of different, like this is also from the New York Times, women's versus men's median weekly earnings. This would be the line of equal wages, and you can see that women only make more than men in like one to three jobs, and most other jobs here, women make less. What other visual variable other than position am I using here? Color, yes. And color here is used for categorical for these like professions, and we can see that management and business, the blue ones are like, which are like in the higher range here, is where women actually underperform significantly in terms of what they get paid. Position is also, like every good thing that I say about position only applies to 2D position. Does not apply equally to 3D position. So for example, like, what's the value of this dot here? Like in a 2D scatter plot, it would be easy to read, but in a 3D scatter plot, it's really tricky to read. I'm not saying that 3D scatter plots never have had any value at all, but very rarely. So 3D is like, we'll talk more about this when we talk about designing visualization. 3D comes with a lot of problems, like perspective, distortion, like shadows, and we talked about all the effects that we have when we use lighting, which we need to kind of give people a 3D perception, and so on. So length and size is good for 1D length, like the length of a bar chart. Okay for 2D, the size of a bubble, or the size of a square, and bad for 3D. So like the volume of a sphere, mentally comparing to volumes of two spheres is something that we're really not good at. You should also know that if we use aligned bars, as I mentioned previously, we're actually using position and size redundantly. Only if we have unaligned bars, like in this example here, do we use just length or size. But generally speaking, just about 1D length, yes, it is selective. We can tell them apart. Yes, it's associated. These are the items of the same size. Yes, it's quantitative. We can make judgments about magnitude. We can make order judgments, and we have a fairly big vocabulary of those of length and size. So here is an example that we'll look at more closely at some point. Here we have like the budget, the 2013 Obama's budget proposal, and here size is like the different, let's say, types of spending, and that all shown in one big bubble chart. We'll tease this chart apart at a later point in more detail. Then we have value, luminance, or saturation. So basically, how bright or dark something appears as a color. This is okay for quantitative data when length and size are already used, but it's also really tricky to recognize many shades. So like, I can easily tell apart like 50 different positions or lengths, but I have a hard time telling apart 7 or 8 or 10 shades of gray. So the length here is quite limited, but it's somewhat quantitative, although there are problems, and it is ordered. So like clearly not quite as good a channel as position and length. So here we have an example of a diverging value scale where we use saturation or value to encode like the win percentages in the Obama-McCain election on a geospatial map. And we'll talk more about like the pros and cons of these kinds of maps in our map lecture. Color is good for qualitative data, for identity channel. This is an identity channel. We have a limited number of classes, and we talked about color in the perception lecture a lot. So usually you should never use more than 10 colors, and you have to be very, very careful of how you design a visualization with 10 colors. Usually you should limit yourself to 7 or less. It does not work at all for quantitative data. So here we have the comment that we need a legend, right? That is tricky because it's not intuitive. Like then you have to really compare for the legend, so you can't really make intuitive judgments about a magnitude. And as we talked about, there's many pitfalls. If you use color, my rule for use of color is to minimize color use for encoding primary data and use color for these pop-out effects to highlight things. Use it for brushing and for highlighting and so on. And so is it selective? Yes. Is it associative? Yes. Is it quantitative? No, clearly not. It's also not ordered. So the green is not smaller or bigger than yellow. And the length is limited because we have only 7 or 10 classes here. Here's an example of the estimated fraction of precipitation loss to evapotranspiration between 1971 and 2000. And so that is like a bad color scale. It's good in terms of it's very, like it shows us like many different values here. So we can like, if we exactly want to pin down like Salt Lake City, Salt Lake City is green, I can look up that means 0.7 to 0.79. But it's not so great because it's just not ordered, right? So here, for example, when you look at this chart, you would assume that the dark value here is maybe higher than the blue value. But if you go to the legend, you'll see that the blue value here is actually higher than the dark value. So this is kind of like an example of how the color like isn't ordered. So it's good if you need precise lookups, but it doesn't really give you like an overall impression of the data. Here's this example that I showed at the first lecture, which is a good example of the use of color. I'm using color here to call out like one selective attribute. Are those players active or not? Shape is great for recognizing many classes. So I think shape has the largest length of all of the visual variables. Like we can tell apart shapes very easily, but it doesn't support grouping, right? Or not very well, let's say. And it doesn't support ordering. So it's selective, but it's only limited associative. Maybe I can say things that are pointy belong together compared to things that are round, but that's not a very good thing to rely on. It's not ordered, but as I said, we have a lot of different of those available. So like here are a couple of shapes, and I'm showing you like 150 or 200, and you all know those shapes and can easily tell them apart. But of course, they don't convey a variable intuitively. You have to learn them, and you've learned all of those, or many of those shapes. We can associate meaning with them, but it's a learned thing. It's not like length. We know that something that is higher is more than something that is smaller. Somebody tried, a Harvard statistician tried, so it turns out that we are actually extremely good at seeing subtle changes in facial expressions. And so Chernov thought, well, we can use this skill that is baked into us evolutionarily. We can use this skill to encode like up to 7 dimensions in these little smileys. And so this was actually there is a discussion about this at this link. I'm not going to go into the details. So they map 7 properties or 7 data values on these shapes. Like how round is the face, how smiling is this person, how long is the nose, what is the distance between the eyes, what is the position of the eyebrows, and so on. And so why doesn't this work? Like, is this bigger than that? Why is this broken? Subtle?
Feels like pieces of data are split across so many different
Yeah,
parts of the presentation.
exactly. So the data is faithfully represented, but we just can't read it without really like teasing it apart and very consciously looking at one of those faces and then trying to think about what is the meaning of it. So it's just not very accessible. And so this exercise that we did at the beginning, other people have thought about this. Here is a paper, here's a web page that came up with 45 different ways to communicate two quantities. So writing or notation, squares, repeated icons, different cypherspheres, bars, and so on. We get into more esoteric ones a little bit later, like here shapes, or icon surfaces, or heights of icons. And these are all possibilities, but like this is an interesting piece. Fat fonts, I'll talk more about that in the map lecture. These are possibilities, but they're of course not all good choices. And so, why are they not all good choices? Why are these quantitative channels especially different? It turns out that when we do like a perceptual experiment, we can find out that the physical intensity of a stimulus is not for all different types of stimuli linearly correlated with the perceived sensation. So what that means, physical intensity, is like I want to encode length 2, that's our physical intensity, and how do we perceive length 2? Gesundheit. How do we perceive length 2? And so the only visual variable where we have a linear relationship between physical intensity and perceived sensation is length. So here, 5 maps to 5, 4 maps to 4. For all of the other ones, like brightness, we tend to underperceive the we tend to underperceive the sensation. So first, physical intensity of 5, we perceive it roughly as 2. For saturation, we tend to overperceive it. For electric shock, which is not a recommended data encoding, we tend to way overperceive electric shock. So like a small increase in the physical intensity of the electric shock is very painful. And so this goes back to, these are called Stevens' psychophysical power law. And that's here like sensation is intensity to n. And this original study also did, like this is kind of the version that we use if we want to talk about visualization, visual data encoding, and make a joke about electric shock. This is the encoding of all of our senses, the original paper. So this from previous figures from our textbook. This one is from the original paper. And here we have smell, not a very interesting data encoding. Loudness is also, we perceive loudness, like we underperceive loudness. Brightness, volume, area are ones that we covered. Taste, we tend to overperceive the intensity of taste. Heaviness, like objects appear heavier, not in a linear relationship. And then the electric shock here. This is one of my favorite exam questions, by the way. So, little test. How much longer is speed in A? Just shout out a number. Twice as long. Correct. How much longer is speed in A? A year, 4 times, 5 times, both pretty close. How much steeper is A than B? I don't hear any consensus. Because somebody want to say 3? I hear 3. It's about 4 times as steep. How much bigger is B than A? 4, 5, 3. So notice how everybody agreed at position size. Like everybody got it right. Here it's about 5 times as big. How much bigger is B than A? 8, 3, 7, 4, I hear 2 times. But I'm cheating here. It's 2 times by diameter and 4 times by area. So that's a problem though, because like if you look on the internet, you will find a lot of infographics that encode something as the diameter of a bubble, which is a terrible idea, right? Because you misrepresent the value actually quite a bit. So how much larger is B than A by area? 3 times. So it's like twice. Yeah, it's really hard to tell. How much darker is B than A? 3. It's about 2 times as dark. How much darker is B than A now? That's a lot. 8. It's about 3 times as dark. So what we can see here is that the precision of how we can perceive those channels is really quite different. And kind of related to this is this game, this eyeballing game here, where I essentially have to position something in space, which I think is correct, and see how good I am at judging things. So I'm actually quite good at doing things like position, but then here bisecting an angle, I'm actually off a little bit, or making the point equidistant to the edges, off a little bit, but not too much. Marking the center of a circle, that was good. Making a right angle. So what we can see here is that angle judgments tend to be a little bit difficult. Here you find the point of convergence, and so on. So you can play with this, but here this kind of leverages some of these properties, and you can test yourself how good you are at spotting those. Of course, there's other factors that affect our accuracy and how we perceive these things, especially alignment, distractors, distance, and common scale. So alignment obviously is like this versus this. Is it aligned or unaligned? But then it's also, we can say, is something unframed and unaligned, like here, or is it framed and unaligned? And so who would agree that the framed unaligned proportions are easier to judge than the unframed unaligned? Who would disagree? Few people. Most people have no opinion. So my personal impression here is that framed unaligned is much easier to judge than unframed unaligned, because we have a proportion to compare to, right? We can see the white area versus the blue area for these 2 different cases. And then unframed aligned is of course the easy case. And then distractors. So if we have other things in between 2 things that we want to compare, that has an effect on making judgments. Or distance. So those 2 bars, they're actually the same 2 bars, and you can see that there's a maybe 5 to 10% difference between them, but it's really hard to see that when they're all the way apart here, even though they use position on a common scale. So all of these things affect accuracy. And so now people have studied this. This is a figure from the seminal paper by Cleveland and McGill, where they studied these accuracies across many different conditions. So for example, here we have our aligned bar chart. And the question was to evaluate the magnitude of those 2 bars, how many percent is the left one from the right one, how many percent is the left one from the right one, left one from the right one. So here we clearly have distractors in here. Here we have an unaligned scale, and then here we have 2 things sitting on top of each other. Similarly, comparing pie charts to bar charts. And so this study kind of gave us these insights on where do we make errors. And you should be familiar with that study, because that goes back. This was replicated in this paper that I asked you guys to read for today by Hare and Bostock, crowdsourcing graphical perception. Okay, so now I want to discuss this paper. Who wants to give a summary? Yeah.
So these guys wanted to see if they could use crowdsourcing as a means of exploring graphical perception. Specifically, they used Mechanical Turk, an Amazon thing. So they tried a bunch of different experiments that some other guys did earlier to see if they got the same results. They did overall get the same results, and they explored to what extent those results were valuable from crowdsourcing.
Okay, great. So has anybody run a Mechanical Turk study? 1 person, or one of our TAs, 2 people? So what's Mechanical Turk? Yeah.
it's a little like an online job thing where you just do little things that some guys set up for you in a very specific way.
Yes. So Mechanical Turk is a website and like a crowdsourcing website. There's others, of course, that allows you to give out human intelligence tasks. Has anybody done like a human intelligence task before? A couple of people. Some of you might have done these gamified ones, right? Where you play the game to help, for example, some like machine learning tasks of image labeling or anything like that. Mechanical Turk is like that, but instead of making it fun, they pay you. Okay, so why is it interesting to use Mechanical Turk to run an experiment like this?
Because there'll be a lot more cost involved when it's a lab-oriented study, and there'll be some other factors that are involved on Mechanical Turk, but it will be a wider reach for the experiment.
Yeah, so we have cost as an important factor. We can run an experiment quite cheaply, reach, because one problem of many academic studies is that they are tested on people like you guys, like on students at a university, but don't sample a broader population, right? So that's a bit of a problem of generalizing it. I wouldn't say that Mechanical Turk generalizes to the overall population, but it's a little bit broader at least than what we have in a classroom. Other benefits?
They're able to reduce the amount of time it took to run a single study.
Exactly. The amount of time, especially the amount of time that you have to actively be there and supervise an experiment. If you ever run a lab study, it takes 2 weeks full time as a graduate student, for example, to get 100 experiments or something like that. You have to schedule all those people, you have hundreds of emails and so on. And if you push this to a Mechanical Turk, all of these problems are solved for you. What are potential problems with Mechanical Turk that they identified here?
We do not have control over the many parameters or something. The person taking the test may not have the same motivation that we have.
Yes. So it's tricky to measure motivation, because if I'm in person in a lab and there's a supervisor sitting next to me watching me do a task, I'm not going to go on Twitter and read Twitter tweets. I'm going to focus on the task, and so timing is an issue that they brought up, right? So anybody remember what they expected and what they got in average time for a single task? Yeah.
I expected 10 seconds per task, and it was often 9 minutes.
Yeah. So it was minutes instead of 10 seconds, what you would usually expect in a lab setting. So other problems with Mechanical Turk other than subject motivation?
You don't know the screen now.
Exactly. So in a lab, you would have a very controlled environment. You can calibrate your monitor. You can you can make sure that everybody has the same viewing distance, everybody has the same angle, that there is not different lighting conditions, and that of course doesn't apply on your personal computer. But is it always a downside?
No.
No. Why not?
Because it adds generalization.
Exactly. This is what we call ecological validity. So we increase the ecological validity of a study that we conduct like that, because we'll get a sample of how people actually use their computers and not just our own computer. But of course, it depends on the question that we want to ask in a study like that. If we really want to have precise results and very small error margins, then the lab setup where we control everything is good. But if you also want to have some ecological validity, maybe such a setup is not all that bad. So what are the 2 studies that they replicated in this experiment? Or any other pros and cons that we came up with? Yeah.
One other con was the restrictiveness of the platform, so they weren't able to render. They had to use some embedded frame to display
Yes.
their own data.
Exactly. So Mechanical Turk has standard interfaces for things like survey questions, but if you want to use something interactive, then you usually have to use your own implementation. What is the benefit of your own implementation?
Screen parameters.
I can query screen parameters, and I can maybe also control the timing a little bit, right? Because I can measure when people actually work on something. You can do this like ready, steady, like ready, go, and then really measure time until the task was completed. So what was one of the important like caveats about like what should you always do if you run a Mechanical Turk study?
But one thing they did is they did kind of like a pre-test to see if you were qualified to make a judgment on whatever the...
Exactly. Qualify in terms of ability and understanding, but also, I guess, in terms of motivation, right? Because it might be faster to just not give good answers and just to click and just wait for the money to come in. But if you have some verifiable questions that you automatically check against and only like let people proceed with a task that actually pay attention and answer this correctly, then you are likely to get rid of these problematic cases. And so in the paper, they reported that they could cut these like incorrect answers from 10% without any of those qualifiers to like 0.5% if I remember correctly. So what were the studies that they ran? Yeah.
One of them was the proportionality study of spatial encodings.
Yes.
The second one was transparency and luminous for adjustments of chart grid lines.
Okay, and so could they like replicate the results? Somebody from this side want to answer? Yeah.
If I remember right, they got really good results that were pretty similar to what they get in final lab. And
Yeah.
they suggested doing that in addition to using Mechanical Turk, like running your own in-lab stuff just a lot smaller just to make sure that things are still lining up.
That's definitely an option. So they could actually replicate the results of those two different studies. They also added an additional component to one of the studies. Anybody remember what that was? On the far left, anybody?
Was it payout? How much they paid to sample the study?
Yes, they also they discussed how much they paid. And so what did they actually find with payment?
It was not necessarily better.
It was not necessarily better? What do you mean by that?
It seemed like, if I remember, there was one study that paid 8 cents instead of 2 cents per click, and the results were not very consistent.
So essentially what they found is that the quality doesn't change with how much you pay, but the speed did change and how fast they had the results. So if you really need to get your results in 2 days, you just can pay more and you'll get more people doing it, but it doesn't have an effect on quality. So that was one aspect. And how much did like they pay on average per hour? Do you remember? So it was some like trivial amount. And I'm basically saying this because it was way below minimum wage. And of course, like you probably can get away with that in running a study, but if you ever as a grad student run a study like this, you should also think about your ethics, right? You should think about how much you pay, and you should pay, in my opinion, at least $15 an hour, because that's what you usually like have a minimum wage in many places. And not only is it the ethical thing to do, but also a reviewer like me will complain a lot if you underpay your subjects, and so your paper might get rejected. Yeah.
But isn't that they underestimated all the
They underestimated it, yes. So like I'm not faulting them because they assumed like they kind of like they give us guidance. But essentially what they could have done is they could have like after their pilot, they could have seen, hey, actually it takes a lot longer than we expected. And maybe they should have adjusted it. But of course you could also say, okay, people take 50 seconds because they're like on Facebook at the same time. Maybe then it's not justified, right? So it's a gray area, but it's an issue that especially if you publish in Chi or in a BIS conference, you cannot like pay not a living wage for a study like that. So you have to talk to your PI and tell them, hey, like you need to pay those people at least roughly like $15 an hour, and then it's fair. And I think you should use like your home country as a reference and not the country where those people are from, what is like an acceptable wage there. Okay, let me see. So yeah, I personally think that Mechanical Turk is a really great platform for doing these kinds of studies. Anybody want to comment on their methods, like the statistical analysis? Did you find that rigorous? So how do they report their data? Like, do they show you bar charts with error bars and then highlight the ones that are significant? Or do they use a different method? So they do highlight significant sometimes, but what they mostly do is they give you the data, like the average value plus a 95% confidence interval. And that's kind of like, many cases nowadays, the preferred way of reporting these quantitative statistics, because it lets you like easily judge a combination of like how certain are you about the results and how big is the effect, right? And so what you're looking for is like, if you look at something like Figure 8, you have very narrow confidence intervals for the white plots, and then pretty wide confidence interval for the dark plots. And then you can essentially judge, okay, if I have like no overlap between 95% confidence intervals, I'm pretty sure that this is not a random effect, right? I'm pretty sure that this is a real effect. But I can also quantify how far they're apart. And so it's not just about some minuscule but highly significant effect, but I can judge kind of like the likelihood that an experiment was run, or the likelihood that the effect is really there, and the magnitude at the same time. So it's also a good paper in terms of methodology. So if you run a study like this, you can use something like this as a reference. Anybody want to like say something else about this paper? Yeah.
I just want to say something about, I think those before. So when they report the error rate, so they use the low scale, but so which like makes the error rate actually small.
Yes.
So when you look at it, it's small, but actually if you take the actual number, they're actually bigger.
Yes. So they use a log scale for the error. Why do you think they did that?
They want it smaller error rate.
Yes. I think one reason of that is I think it's justifiable, but of course also the original paper reported it like this, right? And they did a replication study, and so that's why they also did that. But yeah, I think that's a good point, and it's something that you need to be aware of when you look at these charts. So here are these log error rates that you mentioned here, and so like if you look at this, we can clearly see that the log area, like the first task, 3 tasks here, are positioned on an aligned scale. And we can clearly see that the log error here is quite low. Things very close together are, according to Cleveland and McGill, have the lowest log error. They did not quite find that effect, for example, here. They didn't find a strong effect in the crowdsourced results. So basically here, because those bars between the first and the third one here, they overlap, so you couldn't make a conclusion that we absolutely know that the task 3 is more error prone than task 1. But we can make a conclusion that here these 3 are on a line, on a common scale, and these 2 here, task 4 and task 5, are on a different scale. They are clearly, like, except for task 3 here, they're clearly different. So we can make a reasonable judgment that there is in fact a difference of how accurate we perceive them. And then you can see here that the bubble charts, task 7, are actually, in terms of log error, they're quite off the charts, right? And so bubble charts are extremely popular. If you look at things like the New York Times, I've shown you examples today. They're popular because people like circles. But they're not necessarily very accurate. But also like squares by themselves, so that the size of circle, size of square are not very accurate. And by running these kinds of experiments is how we came up with the ranking of these, like what are the best channels or visual variables for these different data types. And so this is a figure from Doug McInlaw, and he splits it up between quantitative, ordinal, and nominal, whereas like our textbook only does it for magnitude and identity. This is more of like, this is pre many of those studies. that go into more detail, but it's still a good guideline. And this is what we have in our book, and I think that is like a quite reasonable list of things and a quite reasonable ranking, like effectiveness from most effective to least effective. So the last thing I wanted to talk about today is separability of attributes. Can we combine multiple visual variables or channels? So we can combine position and hue. These are like fully separable, like whether a dot is red or blue doesn't influence where it is in our perception. We can, to some degree, do that with size. So there's some interference though, because the precise position of a very large bubble is harder to judge than of a small bubble. So there is some interference there. Width and height, we have like, I would say like quite a bit interference here, like between position and width and height. So we have to kind of like mentally find the center of a shape, for example, to properly position that. And here I'm encoding 3 data points in addition to the position data points, one in the red channel, one in the green channel, one in the blue channel. Is that a good idea? Obviously not, right? Because this is not how we perceive color. We don't have like 3 separate channels that we see on here. And so that's clearly not a good idea. So that's it for today. And I'll continue on Tuesday with like more on E3. And on Thursday we'll have another theory lecture.
Either way, I wouldn't mind for this. I haven't done it yet. Yeah, I'll need to do it too. I don't have any other plans tomorrow. I should have worked on it more yesterday. But I think probably yeah.
Did you get it, Alex?
Yeah, I think so. It's a little bit weird.
I think this would be fine. I don't know exactly.
Yeah.
That's when I was like,
yeah.
Well, your guy was something else, though, right?
it's double.
So
it's like I dealt with recursion and like and like had to deal with variables and stuff. This is like, so the first one's super easy, it takes like 30 seconds. Because you should this one, the second time is like skipping around, but like you go down and you have to pass the position back up. And so like that's when I was like, oh.
Yeah, it's a little bit weird. Because, and it's not always clear based on the position how much further down it should be.
Exactly. That's
so,
what it's like. But,
So
that's whenever I would pass it back to my role, it would be like, 2. I'm like, no, you're supposed to be 3.
Yeah, I had some off by 1. And
Yeah.
It's a little bit weird.
Yeah, that's my fault. I should have gotten
the T3 stuff.
I mean, I've been using T3 for a long time, so
I have not.
Yeah. It's pretty intuitive.
I went to the lab because I thought they were going to talk about like the second
yeah.
Like,
so the lab thing, that's what they do every week?
Yeah. Well, it'll be announced.
I guess you could have asked, but they didn't really seem to do it.
That's the thing, there's like, you want to talk about recursion, talk about different concepts. And they had one slide that was, what is recursion? And it was just the definition of recursion. And like, how to do it for each recursion. And I was like, if you want me to do factorial, I can do it. Like, I can do any type of recursion. Tower of Hanoi. I'll give it to you. It's so many layers.
That's like CS basics.
Yeah, right. But it's like once you
This specific one was pretty weird, I'd say. Okay.
And that's when I was like, if I didn't know we created it all, the second one would be really hard.
Yeah.
Like I thought it was pretty difficult. Because then it was like, oh, you gotta set it equal. And it's like, I like was just retraining the position, but I forgot to like set it equal to position, and I returned it. So I was like, oh, and it was like sand work. And I was like, that's it. That's why you do that.
Yeah, so you have to keep passing it.
Yeah, exactly. Because it's like, I could get it down, but when I was passing it up, I would lose it, and I was like, why am I losing it? But I wasn't setting it equal and overwriting it, so it's like, I knew every time. It's fine, I'm not bitter, but like, actually...
I'm a little bit bitter too. I spent a little too much time on it.
Yeah, I know. So I was like, it took me a little too long. Oh, is there another call?
Oh, there might be.
Yeah, hang on.